Alright, so in this video, I have some thoughts on coil resistance and the atomic level. Alright, so if I have 41 gauge coils and has half a mega ohm or 480 kilo ohms of resistance between all of them in series, I mean, if you were to say 41 gauge copper wire has 279,100 atoms approximately thick, and that's that's pretty thin, but I mean obviously at the atomic level that's nothing. But now what happens if you start getting thinner and thinner and thinner, where you start getting closer and closer to the atomic level? And if I did the exact same thing I am doing now, obviously the resistance would go up higher and higher. But what if you were to get it to 1 or 2 atoms thick, just like graphene has the superconducting properties? Now, if you did this, if you could possibly do that with copper, which is physically impossible with our technology currently, but if you were to do that, things would start getting kind of interesting, I think. I mean, because I've been running this motor on this capacitor. It's a 4500 farad, 250 volt capacitor. I've been running it for over 4 hours and 15 minutes on that from 250 volts. And as you can see, the voltage is just barely dropping. And a lot of the dropping is from the leakage current from the capacitor itself, but also very little bit from the motor. But my theory is, look how efficient this is on 41 gauge wire. Now, what if you could somehow or another imagine 1,000 gauge? What would that even run like? Obviously, there's 89,000 ish feet between one, or in one coil there's 89,000 feet roughly. So if you had 1,000 gauge, just imagine there'd be like millions of feet of wire per coil. The resistance would be insane, but also the voltage would be insanely high, and it would take such little input to turn it. If you could get a power source that could run at 1,000,000 volts, which would be pretty damn hard, but the efficiencies would be exponential, I feel like, right? Let's say if you had a battery pack that could, supply, let's say, 500,000 volts, and you make a motor out of very, 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 very thin wire, and you're able to switch that voltage without having issues, because I'm having issues with 1,000 volts. I can get this actually around 1,500 now with no issues. By doing so with this coil offset, the two coils are repelling each other, but the magnets are orientated the natural of north and south. So this one fires, it pushes it, and this one's attracting at the same time. So it's pulling it and pushing it at the same time. But yet the coils are both north, or vice versa. They're both facing the same direction. So that is, I think, why there is no arcing or hardly any arcing, even at 1,000 volts. So there's like no back EMF or voltage spikes, hardly any. So now if you could control that with having, with said extremely fine gauged wire, you would need super high voltage, but the input would be such minimal. And there is still torque at these voltages. In the current, I've showed you in the past videos that the amount of current is very small. It's in the very minimal microamps, about 30 microamps roughly. And now if you could step that gauge wire higher and higher with more resistance, or even if you had 1 or 2 atoms thick, then it might become a superconductor, because there's no electrons that are hitting each other. They're able to flow freely. So the thinner the wire, the less impacts of the electron flow there is. theoretically, right? I had another idea too, but I can't remember now. Dang it. But yeah, I mean, if you look, it's extremely efficient. This is, I mean, it's a capacitor. It's not a battery. These are supercapacitors. These have way more storage than a regular standard capacitor, rated in microfarads, versus, a supercapacitor rated in millions of farads. So you can see how little stored energy there is in this capacitor. I know the motor is spinning slowly, but because of the resistance and because of the amount of motive force when you fire the coil, and then when it is fired, there's the assisted magnetic field that is within the coil pushing the magnet, but it's also a generative force. So I would actually like to figure out a way to how to get rid of that, because these coils can't spin the magnets very fast. But it'd be nice if I could figure out a way to get rid of that issue. Man, I wish I could remember what I was thinking of before, because it was a really good idea. It had something to do with the atomic level. If I remember, I'll make another video on that, I think. But yeah, I'll cut this off. But I like this capacitor. I'm not kidding you. It runs 12 plus hours on that, from 250, and it stops around 50 volts. I mean, it's at 4 hours and 20 minutes already. And it went from 250 to 160 in that time. And the lower the voltage gets, the longer it takes to drain. And the leakage current, I think it might get better too as it gets lower and lower in the state of charge. The reason why I want to use capacitors is because it's a direct connection to the motor's efficiency. You're just storing an electrical charge, and you're using that said stored electrical charge just in a capacitor itself. And this is what I was thinking about. That's right. All right, so now it's gonna get a little longer because I just popped in my head. So I was talking about one of my videos about Joseph Newman and his his Newman motor, and he always kept talking about the amount of coil is what matters. And what I think he was getting at is the amount of resistance in the whole system. And obviously, if I were to scale this motor up substantially, if it was the size of a house, the coil gauges could be thicker, and you could get more of a stronger magnetic field with less, power input. Or, if we were to use 41 gauge wire for the entire thing, you'd have like a couple million ohms. Or I should say a couple million mega ohms, because that 1 million ohm is I think that's 1 mega ohm. But yeah, what he was getting at is the amount of resistance and back spikes you can collect off of that is what is important to his design. Motor, he kept telling you that a motor that runs on current depletes the battery, because the stored energy in the battery is you're taking the charge, which is the current flowing through the wires, and you're pushing that current through the wire to the motor, and that's doing the work. Now, when he was saying, when you do a voltage system like I'm doing, I'm using very, 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 very little current, but a lot of voltage. I'm just using the pressure of the system. There's hardly any current being transferred. And that's why this capacitor can run for so long, because there's hardly any of the electrons flowing out. It's just using the pressure of the capacitor charge. That's the theory around his motor, I think. And that's why I'm kind of going down this rabbit hole of high resistance motor, pulse motor. And I kind of think he was onto something, to be honest with you. And I mean, he got shut down. And I mean, who knows? It could have been fake, but I mean, I don't know. It seems pretty legit to me. I mean, look at the amount of time this video has been, 10 minutes now, and it's only at 159.5. And we're at 4 hours and 23 minutes, 24 now, pretty soon. But if you can get something to run on voltage, that's what's important, not current, because if you run something on current, you're going to drain the system's source. Now, if you use voltage, you're just using the pressure of the source, and that barely drains any of the current. Now, the thing to work on is to get rid of the back motive force on the coil, which is, Lenz's law, which is going to be really hard to get rid of if you can, which probably can't because of the laws of physics. But yeah, I'll leave this as it is now. I am got a lot of work to do on this motor and my ideas on it. Alright, see you later.